Hi everyone, this is Professor Majumdar and you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'm going to perform CFD aerodynamic analysis of a car by using SolidWorks Pro solution. You can see the car, this is actually Ford Mustang car. This is a muscle car from Ford. You can see the model, it is having a length of 4.75 meter and width 1.75 meter. It is the actual model. In this analysis we'll find out the drag coefficient and also full force. In aerodynamic analysis, drag force and pull is very important. On the other side, if the lift is high, there will be less contact between the car wheels and the road. In that case, the stability of the car will be actually disturbed. The perfect contact between the car wheels and the road will be less if the lift is more. Therefore, while designing a car, we should take care into these factors, like it should have less lift force and also the drag force and drag coefficient will be less. Actually, in case of sports cars, coefficient of drag is very high. Generally, in case of cars, the coefficient of drag is varying from 0.2 to 0.7, and especially in case of Formula 1 cars, the drag coefficient is actually ranging from 0.7 to 1.1. In normal cases, the coefficient of drag should be very small. Actually, this drag force depends on velocity also, right? In this aerodynamic analysis, we'll carry out two different analyses. First one, the car will be moving with a speed of 50 meters per second. It is approximately 200 kilometers per hour. And the second case, speed will be reduced. It will move with a speed of 30 meters per second. And we'll compare these results and see at which velocity the different parameters like coefficient of drag, lift force, frictional force, etc. and see which one is more efficient one, right? Actually, this efficiency you cannot say in this way. Based on requirement, you can say these values will be there. In case of Formula 1 cars, the drag coefficient will be very high. It will be up to 1.1, right? So without further delay, let us start our analysis. You can see this is the car. It is a very costly car. It is a muscle car from Ford, and on road in India, it is having a price of approximately 93 lakhs, right? Okay, so let us start our analysis, and we're starting this analysis from here, flow simulation, and the flow simulation environment will be created with the wizard, and we're keeping the name of the project as default project 3 because we have already performed two projects with two different velocities or two different speeds. So the default project name is project 3, and from unit system we're considering this one standard unit as SI, and from different parameters we're considering pressure in Pascal, velocity in meter per second, and length will be in meters. But at the same time, temperature we're considering this one as degrees Celsius, though in this case temperature is not that much of important. Anyway, we're considering temperature as degrees Celsius. And next to that, we need to consider what type of analysis it is. Definitely, it is an external analysis. So let us check in with external analysis, and we need to consider physical features. We need to check fluid flow, and gravity will be involved in this case. You can see direction of gravity in this case is Z. So along Z, it will be minus 9.81 meter per second square. Next to that, we need to consider fluids, and in this case, our fluid will be air, and it will be laminar and turbulent flow that will be determined by the car itself. So let us move on to the next step. And here in this case, we are considering default wall thermal conditions and roughness. Next to that, finally, we are considering thermodynamic parameters. Pressure will be 101.325 Pascal and temperature is 20.05 degrees centigrade. And here in this case, the velocity parameters are very important. Let us see in which direction the car will be moving, right? So you can see here, this is the car. So when you see from this direction, car will be moving in the opposite direction of X. You can see here, right? Therefore, air will be moving in the X direction, right? So in this case, in the first analysis, we can see the velocity of air will be 50 meter per second along X. That means the car will be moving in opposite direction of X, and the velocity of the car will be minus 50 meter per second. So with these conditions, let us finish this. Now computational fluid domain is created. Let us see this one. it is preparing model geometry because the size is very big one, and in CFD analysis, more the computational domain, it will take more time for analyzing or calculating. Now fluid volume is being recognized. You can see this is the computational domain. So our task will be to reduce the domain because more the volume, it will take much time for simulation, right? So our task will be to reduce the domain. So edit domain, and we can reduce the size by dragging itself, right? And we can do this one from different planes. Let us select different orientation for this one. So this is the domain, right? This is good enough. Let us hide this domain. Next to that, we need to apply different boundary conditions. We have already applied one, that is the car will be moving in the opposite direction x with a velocity of 50 meter per second. Now we need to provide some other boundary conditions. That means we need to provide rotation of the wheels, and you can see here the car will be moving in the opposite direction of x, right? So air will be moving in the x direction. Now to provide speed of the wheel, what we'll do is that will be obtained from boundary conditions. Let us apply boundary conditions, insert boundary conditions, and it will be coming from walls. It will be wall motion, and in this case we can provide either linear velocity or angular velocity. In this case, there will be some kind of relative motion between the road and the wheels. So the road will be moving in x direction, and its velocity will be again 50 meter per second. By the same time, the velocity of the wheel will also minus 50 meter per second. It will be equal in magnitude but opposite in sign, right? So initially consider the velocity of the road, that will be minus 50 meter per second, minus 50 meter per second. We need to select the road again, select it, green check, done. Another boundary condition to be applied, that means the rotation of the wheel also to be applied, right? So again apply boundary conditions. From here, insert boundary conditions. It will be walls and wall motion we're considering, and in this case the rotation of the wheel will be either angular velocity or linear one. We're considering this one to be minus 50 meter per second, and we need to select that wheels. That wheels can be selected from the geometry itself. So we can move on to the geometry, solid bodies. We have already provided specific names for these wheels. Let us select solid bodies. These are specified as wheel 1, 2, 3, 4. Actually we're having 2 set of wheels for each one. Then it will be again different parts will be there, right? Again we need to select wheel 3.2, 1.2, 2.2 and 4.2. So 8 wheels are there. We have selected 8 wheels, and the velocity of the wheel will be minus 50 meter per second. So grain check, done. So we have applied necessary boundary conditions. Next to that, we need to select some goals, right? It will be global goal. By the same time, we need to find out some kind of surface goals and also equation goals. From equation goals, we will determine the coefficient of drag. That is very important in case of this aerodynamic analysis, right? So starting with goals, insert global goals, and in global goals, we'll select total average pressure, and also we need to select that lift force, that is force in the z direction, and also need to select average velocity, and also we need to find out force in x direction. You can see here x direction means actually drag force, and also we need to find out force z, that will be actually lift force, right? Excluding that one, we can find out frictional force also. So we have selected some specific goals like average total pressure, average velocity, and also force in x direction, that is actually drag force, and force in z direction, that is actually full force. Excluding that, we found this frictional force also. Therefore, 5 different global goals we selected, applied. Now we need to select some other surface goals also, right? So goals, insert surface goals, and we need to find out average pressure on the surface of the vehicle. So you can select average total pressure, and you can select the specific surfaces of this body. Let us select that surface from the geometry itself. We are selecting from the solid geometry or solid body. Selecting the first one, and then with the shift button on, you can select the last one. Let us rename those things, right? The equation goes total average pressure. This is average velocity, global goal. Next one is average force in x direction, that is known as actually drag force, right? You can change this one as drag force. And force in z direction, that is actually lift force. Now the last goal, that is the equation goal, to find out. And in this equation goal, we need to find out coefficient of drag. That is very important for this aerodynamic analysis, right? Insert equation goal, and we need to have this one within absolutes, because this coefficient of drag is not having any unit and it should be positive. So we are starting this one with absolute, initiating this one with a bracket. It will be 2 multiplied by drag force, and that drag force can be obtained from the goals. Then you can close this bracket, divided by bracket initiate density of air equal to 1.225 kg per meter cube, right? 1.225 kg per meter cube. Density multiplied by velocity square. Velocity of the car is actually 50 meter per second, so it will be 50 square multiplied by projected area of that vehicle. We have already determined this one using some method. I'll show that one. You can see here the projected area is actually, the projected area is in millimeter square, that we converted to meter square. So it is 2.4 meter square, right? And we need to find that value of this 2.4 meter square. And finally, we need to provide another bracket. Done. This is equation goal, and we can rename this equation goal as coefficient of drag. So we determined all the goals. Next to that, we need to go for meshing, and let's start with mesh. global mesh, and we can initiate this one manually, and we can degree of refinement can be increased. Let us see the display refinement level. It is defined up to level 1. You can see this is meshing, and we need to increase the refinement level. Let us refine this one up to level 4. So this is okay. This type of meshing is good enough, right? So apply, again check, done. Now to run this one, we have already done this, and that results can be obtained from project 1. After getting project 1, we have done another analysis that is under project 2 with the different velocities, right? We have already done this one. Let us see the solver window, what it is talking about. You can see the solver is finished, and you can see the different results. You can see here coefficient of drag is actually 0.66, and as I told before, coefficient of drag is variable for different types of cars, and even it is dependent on velocity also, right? Formula 1 cars, this coefficient of drag is in the range of 0.7 to 1.1, and in different cases, other different cars, it is ranging from 0.2 to 0.7. And in case of our this Ford Mustang car, it is actually in the range of 0.46, right? But it is variable, it is dependent on velocity also. We'll see these results with a different velocity of the similar type of analysis. So we'll check it, and the average total pressure is almost similar compared to the normal atmospheric pressure. It's a little bit of increased, and average velocity is actually 46.64 meter per second. We started with the velocity of 50 meter per second, but here is some reduction in velocity. And friction force, you can see it is 199.74 Newton, and lift force, it is very high, it is 1.115 kilonewton, and total pressure is also equal to atmospheric pressure. So we don't see that much of changes in pressure. We can see variation of velocity and also lift force. Excluding the lift force, you can see drag force is also very high. You can see drag force is actually 2.428 kilonewton. That is also very high. This drag force and lift force should be reduced. Actually, in case of this Formula 1 cars, this drag force is very much unwanted, because in Formula 1 cars, we need to have high velocity or high speed, and this drag force is opposing that speed, right? So to obtain a high velocity or high speed, this drag force should be reduced, and that one can be done by changing the aerodynamic shape of the vehicle, right? So we'll see all these things while analyzing these things, right? Let us close this one, and we'll see the results from different cut plots. We'll see velocity, pressure distribution, and also we'll see dynamics of flow particles from different planes. Let us close this one. So results loaded already. Let us see the results from cut plots. Insert cut plot, we want to see from different planes, right? Let us see this one from XZ plane, and want to include contours and streamlines also, and it will be conducive velocity. Green check. The result is being generated. You will see cut plots of pressure and velocity from different planes. First one we'll see from XZ plane, right? It's done. Now you can see it from cut plot 1. Let us play. It is better to see from different orientations. You can see that at the starting point where it is striking the bonnet of this car, in that case velocity is very less. It is in the range of 6 to 13 meter per second, and you can see the velocity is very high above the car level. And beside also, at back side also, you can see velocity is very less. It is in the range of 0 to 6 meter per second, right? And also the thing is, like, velocity at the top surface is more. It is having some reason, because the thing is we have reduced the computational domain. If you could have maintained the computational domain with high value, then definitely you could have seen different results at the top surface, right? Because if the volume is confined to a specific zone, in that case according to Bernoulli's principle, these things may happen at the top surface. To have the better results, we could have increased the height of this computational domain, and also you can see some kind of vortex is created at the front and the back side. That is actually unwanted, so we need to modify the design with a little bit of changes, because you can see some kind of vortex is created also at the wheels here itself, right down the chassis. Let us change the orientation and see in a different way again, right? This is fine enough, right? Now we'll change the orientation. Instead of this plane, we'll select some different plane, and so cut plot 1, clear and hide, and we want to view this one from different plane, right? So insert cut plots, and we want to see from other planes, right? Let's change the plane from here. We're selecting YZ plane, that's from front side of this car, and here also we're considering display pattern contours and streamlines, and it will be velocity distribution, right? Grade check. Let us play. Also we can see same trend at the side of this car. We can see some kind of vortex is created, and at the top of this car you can see velocity is very high, and also sidewise we can see some kind of vortex motion is created that is unwanted. These two sides we can see some vortex motion, right? And instead of that we can see pressure distribution also, but we will not see that because there is not that much of difference in pressure. Definitely pressure difference is there, but that much of pressure difference we cannot see in this case, right? So we can clear and hide this one. We cannot see that much of changes in pressure distribution, so we'll skip this part, and next to that we'll see flow trajectories. That is the most important part. We're going to see dynamics of flow particles around these vehicles, right? So insert flow trajectories, the numbers of flow particles to be 200, and let us see dynamic trajectories from this plane. Let us play this one. You can see the same trend what we saw before from the cut plots. So we can see some different colors are available at the front side. You can see while the air particles are striking the bonnet, the velocity at that location is actually little bit of less. It is in green zone, and above the car level, above the top surface of this car, the velocity is high. It is more than 50 meter per second, right? And again at the back side you can see the color zone is actually blue. That means velocity is very less. It is below 10 meter per second. And sideways also you can see different color zones having green arrows, which is having less velocities compared to the normal velocity of 50 meter per second. It is less than that, right? Now we change the pattern. Instead of making this one through different paths, we'll see from a specific line or a specific plane, right? So let us clear and hide this one, and we'll see different trajectories. Let us edit this one, flow trajectories, edit definition, and what we'll do is we'll change the pattern of this, right? Let us bring this one to a specific location, and and you can change this orientation also, right? It will be parallel to this one, right? Fine. Brain check. Let us generate flow particles along this plane. It's done already. Now we can see the orientation and see how flow particles are moving along this plane, right? So let's play this. You see along a specific plane how the flow patterns is being generated. It is clearly evident at the back side also. You can see velocity of air particles is very less, indicated by blue color, and at the starting point also it is in the green zone, indicating less velocities. On the top surface you can see velocity is very high. It is in the range of approximately 50 meters per second. In this way you can see flow patterns and at any specific location also, right? Now let us clear and hide this one. Next to that we will see our results from goal plots. So insert goal plots, and we want to export these results to Excel, right? So select all the goals and that can be exported to Excel, or you can check it from here itself again. Let us export this data to Excel. So these are the summary. First one is actually coefficient of drag. You can see it. So we can see here coefficient of drag. It is in the range of 0.66 and it doesn't have any unit. And as I told before, that coefficient of drag is actually different for different types of cars. For Ford Mustang car, it is in the range of 146 to 2.5. We can achieve that coefficient of drag value with the different velocities. Next one actually surface goal, average total pressure. It is a surface goal. It is 101,989 Pascal. Next one is global goal. It is frictional force. After 115 numbers of iterations, it is 199 Newton. Next one is lift force. It is very high. Actually, we need to take care of this one. The lift force should be very less. If it is very high, in that case, the contact between the wheel and road will be very less. In this case, what will happen? The control over the car will be less. You can see here, after 115 numbers of iterations, the lift force is 1.1 kilonewton. Next one is drag force. That is also very high. You can see here, after 115 numbers of iterations, this drag force is 2.42 kilonewton. This is also very high, that to be reduced. Because more the drag force, less will be the speed of the vehicle. So to increase the vehicle speed, we need to decrease the drag force, right? Next one is the global goal, and that is known as actually average velocity. You can see after 115 numbers of iterations, average velocity is 46.64. And finally, you can see global goal, that is total pressure. And here also you can see you cannot have that much of changes in pressure. It is 102,705 Pascal. So these are the different values we obtained from the goal force. You can see all the results from here itself. Let us see that even all the results can be viewed in the form of graphs. Let us see the history. First one is total pressure. It is a global goal. Second one is average velocity. It is in the range of 46.64 meter per second. Next one is drag force. It is 24.28 kilonewton. And lift force is also very high. You can see here is 1.1 kilonewton. And friction force is actually, you can see here, 199.72 Newton. Coefficient of drag, you can see here, is 0.66, right? These are the first set of results we obtained with a velocity of 50 meter per second. In the second project, we actually changed the velocity of the car from 50 meter per second to 30 meter per second. Let us see the results obtained from the second one. Directly we see the results from the goal plots, right? Let us load the results. And we see the final goal plots. Goal plots, insert, and these values are actually based on speed of 30 meter per second. Let us see all the results from here itself, and we can see the results from here. and we want to view these results in the form of graph, right? So let us see the history. You can see here first one is actually total pressure, that is also almost similar compared to the previous one. Second one is average velocity. As I told that we kept the velocity as 30 meter per second. You can see here final velocity here in this case is actually 28 meter per second. Next one is drag force. You can see huge reduction in drag force. Initially it was very high when the velocity was 50 meter per second. In that case drag force was very high. Here in this case you can see remarkable change in drag force. It has been reduced to 873 Newton. After that you can see lift force, that is also very much less compared to the previous one. You can see lift force is actually 333.95 Newton. Friction force initially it was 199. Here in this case you can see friction force is 197 Newton. And this one is average total pressure. It is a global goal. Pressure we cannot see that much of changes. It is almost equal compared to the previous one. And let us see the final one, that is coefficient of drag. It is reduced too much. You can see the coefficient of drag is 0.238, which is very less, right? So from this analysis we could find that the coefficient of drag is actually not fixed. At different velocities we can expect different values of coefficient of drag, but normally coefficient of drag should be very less. By the same time lift force and also drag force should be very less, and these values can be controlled or can be optimized by changing the shape of that vehicle, right? Let us close this one. So with this one we'll conclude our today's analysis. So we performed aerodynamic analysis of a Ford Mustang car, and that analysis was carried out with a velocity of 50 meter per second. And in this case we could find out the drag force and also the coefficient of drag of the car. Next to that we performed the same analysis with a different velocity of 30 meter per second, and we could see that with decrease in velocity the coefficient of drag was reduced by huge amount. By the same time the drag force and the lift force also reduced to a very high value, right? So with this one we'll conclude our today's analysis. Thank you so much for watching this video. Thank you again. Bye.